Hello everyone, today we're going to be talking about abrasive machining. This is you see the oldest basic machining process where we're essentially removing material by using an abrasive grit. That's something that you can do with sand. Sand is silicon dioxide. It's a grit. You can use it to remove material from something that's softer. That's Murray drinking water in the background. Sorry, I'm in a small trailer with two dogs right now. But so we're using a hard grit and using it to remove a softer material from our workpiece. It's a combination of cutting, plowing, and rubbing. Uh, this combination varies continuously, as whether you're actually cutting something, plowing material away, or rubbing material off as the operation continues. So there's really not any guarantee you're getting one of these. And depending on how sharp your abrasive grit is, you might be doing lots of these and not cut a lot of cutting. Whether generally you want to do a lot of cutting. Lots of cutting edges. They're very small. So lots of edges are cutting at the same time. You can get very fine cuts. You can get very coarse cuts too, but you can do really nice finishing with grinding. Um, Excellent surface finish is possible and close dimensional control. So usually when you're talking about needing something down to around a tenth of a thousandth of an inch or better, maybe 2 or 3 tenths, grinding is an attractive manufacturing process for that kind of finishing. It's usually for removing very small amounts of material. So usually you'll use some kind of traditional machining and then do an abrasive process like grinding for doing finishing. Uh, or maybe some really hard materials too, like hardened steel, something like that. After, if you've got a transmission shaft and you've done most of your machining on it and then you've heat treated it and have a really high Rockwell C hardness on it, you might do grinding to finish up bearing races and things like that. That where you couldn't really machine those anymore because you've hardened your material so much that you don't really have a lot of options for machining it. Things like glass, ceramics, carbides, things like that, you really don't have traditional machining operations that work for those. So grinding, you need to grind them with something that's harder than the material that you're trying to machine. So cut tool geometry, you don't have a lot of control over because it's essentially little bitty tiny grits that are going to be bound together. So you have control over the gross geometry of the tool you're using after the little grits have been pressed and formed into a shape, but you don't have a lot of control of the actual cutting edges. So you can pick a grinding wheel, you can pick how it's been dressed, you can pick your machine settings, RPM and feed, you can pick what kind of fluid you're using with it. And a lot of stuff's going to happen as a result of those picks. The force, surface finish, material removal rate, how your wheel's going to wear, how the surface changes, any thermal, chemical effects, and the power required to do the operation. Those are going to be a result of the choices you make. You can use it to clean surfaces. You can use it to shape surfaces, to grind tooling into shape. Uh, you can use it to size things. You can use it to improve surface finish. You can use it for cutoff operations, like a chop saw uses an abrasive disc to separate, to cut as a saw. Different kinds, bonded grains. So if you think about like a grinding wheel, you've got a grains of adhesive or grains of abrasive that have been bonded together to form a solid tool like a grinding wheel. Coated grains. So if you think about abrasive grit mounted on some kind of a backing like sandpaper, where you've got grains that are adhered to some kind of a substrate, and you've got free abrasive machining. So sandblasting, right? The abrasive is free in air. Water jet cutting, where the abrasive is held by water. So, what kind of abrasive materials are commonly used? So, aluminum oxide is very common. So, aluminum oxide, it's common in earth. It's easy to get. It's cheap. It's pretty hard. It's pretty high on the Mohs hardness scale. I can't remember, like somewhere around 8, something like that. It's pretty hard, pretty common material. So aluminum oxide is a very, very common abrasive. There's some other minerals that are used. Diamonds obviously way up there. So that's hard to get. So that's a common abrasive, and we can make synthetic diamonds that are relatively cheap. So that's something that diamond wheels are actually fairly common. Diamond cutting tools, diamond hole saws, things like that are something you can actually get for a reasonable price at a hardware store. It's not something that's very exotic nowadays. Still more expensive than your aluminum oxides, though. So aluminum oxide is pretty common. Silicon carbide, if you need something a little harder, is a little more expensive. Cubic boron nitride, we're talking about significantly harder. And then the diamonds, which will be synthetic in almost all. I mean, there's some natural diamond abrasives, but synthetic diamonds are easy enough to grow, and you want small grit anyway. So there's no sense in taking a nice big diamond and breaking it into smaller diamonds, especially how much you could sell that big diamond for. So lots of little tiny synthetic diamonds bounded together. You can get really, really hard cutting edges. So I get more expensive as the hardness goes up. But aluminum oxide is good for a lot of applications and fairly common. And then again, for harder materials, you might use a harder something like silicon carbide, cubic boron nitride, or synthetic diamond. Here's loose silicon carbide grains. So you can see these are little bitty kind of sharp edge things. You really need those sharp edges on these. These are little bitty tiny cutting tools basically. And so if they're sharp, they're going to cut. If they're round and dull, then they're gonna smear material out of the way. They're gonna rub and plow. They're not gonna cut. So that's one of the things that causes cutting tool degradation is these little bitty tiny grains having their corners broken off. And rounding off. I should say wearing off, because what you really want these things to do is fracture and create new sharp edges. What you don't want them to do is wear into little spheres that aren't going to cut anymore. So yeah, hardness is the key property. You want a really hard grit. And you don't want it to wear. You don't want the edges to get dull or flatten, or your wheel to pack up full of material, and so it doesn't work anymore. Friability, fracture the grits, that's the opposite of toughness. So toughness is the resistance to cracking. You really want your grit to crack and form new sharp edges. If your grit wears and gets round, then it's not going to cut anymore, and it's going to rub, and that's going to make a lot of heat, and at some point in time that's going to cause it to wear even more, and you'll get in a cycle where your wheel glazes and stops cutting. If you've been around a lot of chop saws, trying to chop saw stuff, you see this happen where something will be cutting just fine, then all of a sudden you're still spinning at the same speed, you're still trying to feed at the same rate, but it's just not cutting anymore. And that's what happens when your wheel glazes, is the grit's not sharp anymore. It's rounded off, and you really need to dress the wheel to get it to cut again. Grit size, from coarse to super fine here. We're talking about this rough size of the grits. We'll talk about what this grit size actually means here in a second. But the higher the grit goes up, the smaller. This is essentially grains per inch. It's not really, but it's essentially grains per inch. And then this would be the rough size of the actual grits themselves. And you can see these numbers aren't really the inverse of each other. I'll show why here in a second. So the grit size is the openings per linear inch in the sifting screen during manufacturing. It's not the actual space width. It's not the grit size. It's what size screen they used. So a size number 8 screen would have 8 openings per inch, and that gives you a grain size of 8. The grains obviously have to be smaller than that, hence the discrepancy in why these aren't the inverse of each other. 24 is 24 grains. Again, it's not 24 grains per inch. It's the size used of this. It's how many openings per inch there are, and so the grains end up being a little bit smaller than that, or even smaller, or a lot smaller maybe. This will be done progressively, though, so it's not like you're not just going to start with 24 and get all the stuff smaller than that. You're going to start with the smaller, the higher count number, the smaller grains, and get those selected. Then you're going to select the bigger ones and the bigger ones and the bigger ones until you get the stuff that's too big, and then you're going to go through some processing operation to make it smaller, crush it somehow, and then repeat the process until you've got the grit size you want. Abrasive machining in action, so cutting is really what you want. You want to be cutting chips. Plowing, you're not making chips. You're just creating a lot of heat and mushing material around. Rubbing here, where you've got, this would be linear. This would be more rotating here. You might create some little loaded workpiece material here that sticks on the surface. So you can see this little micro scanning electron microscope view here of a abrasive process here. What you really want to be doing is removing material. So you want nice sharp grits to do that. As the grits get more round, you get more plowing, and you're not making chips. Abrasives can be bonded together to make wheels and other grinding tools. Grinding is a very common abrasive process, and it uses bonded together abrasives. We're talking 1860s here, used to make sewing machine parts. To sharpen needles to make precision parts, you need grinding. Grinding wheel nomenclature, wheel size, abrasive type, grain size, grade, structure, bond type, things like that. And I'll give a naming system here in a second. Grade is the strength of the bond between the grades, from high to or hard to soft. And so harder, the wheel's going to hold together better, and it's going to wear slower. But you might want to expose new grain, because if your grains get dull, then you need to expose new grain. So just harder is not necessarily better, because you might want a softer wheel that exposes newer, sharper grains that can machine a material. But you're going to have to keep your wheel dressed and trued in order for it to cut correctly. So there's going to be a right wheel grade for the right application. Structure. So these are usually porous. They can have from open to dense spacing. You can have little post spacing here where you've got weak posts that are really open, medium posts, or strong posts that are still open. There's usually a little bit of porosity in grinding wheels, especially in the centered ones. So there'll be some open pores in there, and there'll be some specification for how open or closed that is. Bond type, vitrified. This would be some kind of clay or ceramic materials holding the grits together. Phenolic, it might be some kind of a plastic type. Obviously, that would be a softer grade, and these would be more of a harder grade. Silicates, shellac, that would be pretty soft. Rubber, that would be very, very, very soft. Again, I'll post these links in the description below for how it's made on grinding wheels. But here's the ANSI standard naming convention for standard bonded wheels. There's be a manufacturing symbol that's optional. The grit type, so A is your regular aluminum oxide, treated aluminum oxide, some kind of special oxides. See, aluminum oxide's common, right? There's a lot of aluminum oxide wheels out there. Zirconia, special blend, silicon carbide, green silicon carbide, mixture of silicon carbide. Again, most of these are going to be aluminum oxide, with some being silicon carbide. Your grit, basic grain size, again, that's the screen size used to filter it. Your coarse, medium, fine to very fine here. The coarser the grit, the more aggressive it's going to remove material, the worse the surface finish, the worse the dimensional accuracy. So usually you start with the coarse and work your way up to a fine. The grade scale, so soft to hard. The density, so your porosity here, dense to an open grain structure. Bond to the grit type, vitrified, using that clay or ceramic, silicone, rubber, resinoid reinforced. That's like your angle, your cutoff wheels, and your chop saw wheels will be resinoid reinforced. Usually they'll have some kind of a resin, and then there'll be some kind of a reinforcing fiber, like fiberglass or something like that, that's helping to hold the wheel together. It's important for wheels that are spinning at high speed to keep them from just exploding. The reinforcement fibers keep the thing together and keep it from. They'll usually break into big chunks instead of just exploding into a bunch of grits flying in all directions, which would be very bad. It's bad enough when a wheel breaks. A reinforced wheel breaks. You don't want a wheel to just shatter into a bunch of little tiny pieces traveling at whatever their surface velocity was. That would be very dangerous. So here's an example, a green silicon carbide wheel. You can see the numbering system down here. So the GC, it is a GC, green silicon carbide, 120 grit, J grade 5 structure. So if we look at this, it is a J, somewhere on the soft to soft side of medium, 5, somewhere around here on the grain structure. So fairly dense. It looks fairly dense. And then it's a vitrified, so it's a clay or ceramic bond for this. And here's a little 1/4 inch grinding wheel for like an angle grinder. This one's it's kind of hard to read here. A, right? So it's aluminum oxide, 24, so it's 24 grain. Then we're missing the grade and structure, and we've got bond type resinoid reinforced, and there'll be some kind of a resin, and then there'll be some kind of reinforcement fibers in these usually, again, to keep them from just. So what happens when you're grinding with something like this? These don't fracture that often if you have the right size wheel and aren't spinning it too fast, which is why it's got max RPM on it, and that should something you should pay attention to. Make sure your grinder spins at a reasonable speed for these wheels. But usually what happens on thinner ones is you'll bend the wheel, you'll side load it, or you'll get a discontinuity where else it gets loaded really heavily. And these things will usually fracture, and then the fibers will keep it from completely just exploding. It's just good. These can be very dangerous when they fail. So you usually wear not only safety glasses but also a proper shield, and usually long sleeves on these. So it's rotary equipment, which you normally don't want long sleeves on, but for grinding, they're usually very low torque machines at high speed, so the risk of getting something caught up in it actually would probably just stall out if it grabbed your clothes or something. So you wouldn't want long hair down or a scarf or anything, but long sleeves would be fine just to keep you from getting covered in sparks on these things. But you definitely want a face shield on when you're grinding. Oh, and dust mask too. A lot of this stuff, especially silicon carbide, you don't want to breathe. I don't think, I'm not a doctor of that kind anyway, and I don't know about aluminum oxide. I don't think it's a particularly large health hazard. I still wouldn't want to breathe a lot of it though. Um, but silicon carbide silicates, I really don't want to breathe a lot of. That's a big problem in occupational safety and health now, is trying to minimize silicate inhalation. So grinding the wheel itself and then the stuff you're grinding, you don't really want to breathe this. So you should probably be wearing dust masks too when grinding. In fact, I highly recommend when you're grinding to have safety glasses, face shield, and a dust mask. And if you're doing it for a job, you're going to have that anyway. That's going to be required PPE. But doing it, even on home projects, you should probably have the proper PPE when you grind. It's pretty gross stuff to breathe, especially composites. When you're grinding composites, you need to have a respirator or at least a good dust mask on when you're grinding composites. This is a serious deal on composite materials. There's fibers you don't want in your lungs. Here's a different geometry here. It's kind of hard. You wish they just put the proper label on all these things, but it's a C, so that's a silicon carbide, 16 grit, grade, it's an R grade, and then it's a resinoid reinforced. And the shape type 11 here is the ISO type, it's a flared cup. For diamond and cubic boron nitride wheels, a little bit different. We've got a D for diamond, grit size, grade, concentration, bond type, and then some manufacturer special stuff. Working depth of abrasive section. Past that, it's not going to be abrasive anymore, and the wheel's not going to cut anymore. Shapes, the ISO shapes here. You can see straight, recess, two side, tapered, cylinder, straight cup, flared cup, dish, all sorts of different sizes. Straights are the most common, so the straight grinding wheels for cutoff wheels especially, and basic grinding wheels too. And flared cup might be good for certain applications, tapered, dish, etc. Terminology, glazing. So glazing is what happens when your grinding wheel is still spinning at the same speed, but it's not cutting anymore. And what's happened is you have dulled or worn or flattened the grains, and they're not cutting. They're just rubbing. It creates a lot of friction, a lot of heat, and doesn't do a lot of cutting. So that's when you need to dress your grinding wheel, and they make these little dressing tools like this. This is a diamond grit dressing wheel that will get the wheel cleaned and sharpen up the grits. Loading, so some materials load, like steel doesn't usually load, irons don't load. Aluminum will load a cutting wheel, and you got to be extremely careful when you're grinding aluminum. You can load the cutting wheel up, and it just doesn't. Aluminum just doesn't really grind very well at all. There's some safety issues too with grinding aluminum, but in general, some materials don't load, like iron. Iron grinds fantastically, or in all iron alloys, but aluminum really doesn't. It fills up the spaces between the grits and prevents the grit from contacting and cutting. But even your iron tools might load up, and in that case, the solution is again to dress the cutting wheel. Non-uniform wear, when your wheel loses the desired shape, it needs to be trued. So dressing, you're just improving the cutting edges of the grit. Truing, you're actually changing the geometry of your tool back to what it's supposed to be. So truing is when we're actually reshaping it. Dressing is when we're cleaning and sharpening it. So different kinds of truing, rotary cup, rotary disc, a diamond roll, diamond block. So usually when you buy like an angle grinder, or sorry, a bench grinder, something like that, there'll be a little truing or a dressing stick like this that'll come with it, or a dressing wheel, and that's for dressing it. Truing it, you might need get a little bit more aggressive tool to actually dress a grinding wheel. And you're getting rid of cups, you're getting rid of bumps, you're cleaning the tool up, or cleaning your grinding wheel up and getting the geometry back to what it's supposed to be. And you need something that's going to be harder than the grinding wheel. That's usually diamond or something like that for actual truing. For dressing, you might actually just use a roller. So there's crush dressing and roller dressing, where you basically just put some kind of a roller up against it. And what this causes is it causes a surface pressure, and that causes the grains to fracture and expose new sharp edges. So that's really what you're doing with dressing, is you're just really trying to fracture. If you've got like a wheel type dresser, you're really just trying to fracture the grit and get new sharp edges. The diamond ones, you actually remove a little bit of grit and you true a little bit, and but you're also dressing too and exposing new sharp edges. For some real precise operations, you might be continuously dressing or even truing the wheel as it grinds. That's something that can be a little tricky. The one issue when you're grinding is you're removing material from your tool as you machine. So you need to make sure your geometry stays true, and that's hence the reason for truing as you grind. And there's all sorts of special wheel profiles for specialty operations. Again, get expensive. You can see this is a diamond tool here. You can see the diamond only goes for whatever that thickness is there, and then it's on, looks like aluminum or something like that for the backing on it too. Obviously, for specialized industry, it's going to get expensive for things like that. But grinding's pretty common. Grinding's common for cutoff. It's common for sharpening tooling. Anytime it's common for finish machining very hard materials, heat treated materials. So it's a common process. It's a common hand process. It's a common manual, or not manual, like on a manual lathe, a tool post grinder on a lathe for grinding a shaft or something like that down. It's common in CNC machines too. So grinding's a fairly common process. I don't have any slides on it, but grinding is, or abrasive machining is also common in water jet cutting. That's something that's becoming more of a common process. Sandblasting is an abrasive process. So abrasive machining is very, very, very common. So that's it for today's lecture, and I will see you all next time.